Jason is going to talk about production wafer probe at 77 to 81 gigahertz automotive radar applications. Jason Mroczkowski is Director R&D for the Interface Solutions Group, ISG, of Cohu Incorporated. He graduated from the University of Minnesota with a BSEE and holds an MBA from the University of St. Thomas. He began his career in research and development, but he has held roles in product management and finance over the years. Jason has 20 years of experience developing high-frequency test equipment and has earned multiple patents for millimeter wave semiconductor test solutions. Today, Jason is focused on developing high-volume production products for applications from DC to daylight. Jason, floor is yours.
Ramana, thank you very much. And hello all. Thanks for allowing me to speak today. Appreciate the time. And, the topic I'm talking about, I'm sure everybody's at some point in time heard me talk about X-Wave. One thing that's interesting about this particular application is not only the the focus on the trend of automotive radar over the years, but also how this hardware that will be described here has applicability in the new 5G millimeter wave market. So one thing that we gained from our involvement in this application, and I want to thank Jory Twitchell for his input into the material here, and NXP's involvement in this particular topic, because it's not only applicable to the specific application we're looking at, but as we get into 5G millimeter wave and simplifying the environment and the test requirements, implementing BIST and things like that, this very much applies there as well. Jory, keep your hand on that mute button, because if there are some questions about the device and functionality, please, I'm hoping you can help out. All right, so just as an overview, introduction, first of all, we'll just briefly discuss the trend that has happened in the automotive radar device testing market since 2007, actually. And then the latest generation of devices. So there's, large benefits to the way that these devices have come together. But then again, it brings significant challenges into the test application. So we'll briefly describe those. We considered a couple options here, going with a traditional POGO type contactor technology and probe card solution. And then also with the X-Wave. In both of those applications, what I'm describing here is something called Stealth. It's a patent pending technology we're using really to terminate signals directly inside the contactors. And you'll see why this is a benefit and advantage as we go through the slides. We'll talk about the test results. A lot of this material in the presentation, you might be surprised, doesn't focus on the RF characteristics so much, but it focuses more on the mechanical challenges and how we've overcome those. Marty Kaveen has helped significantly to put this material together, and I also want to give a shout out to Chiming from NXP as he generated a lot of this material. We'll talk about the improvements along the way, and then what we are currently doing and have in line for the next steps. So first of all, automotive radar has been around since 2007, I think, was the first instantiation of it. At 24 to 26 or 28 gigahertz, this was more of the proximity sensing, so none of the collision avoidance or adaptive cruise control, but just the blind spot detection, that type of thing. We were able at those frequencies to use pretty traditional contacting technologies and PCB Of course, it was a challenge to bring the PCB structures up to 24 to 28 gigahertz, getting out of the board as soon as possible. The second generation, around 2014 to 2018, took a huge leap from that 24 to 28 gigahertz up to 80 gigahertz. Now this, as I mentioned going forward, just became essentially an RF lab in on the test floor. The devices, they were capable of longer range and increased functionality, but it really challenged the test environment. And now, finally moving on to the third generation, which is the one we'll discuss here today, from a wafer perspective, in 2019 and still ongoing, is a much more integrated version of the automotive radar devices. Again, at 80 gigahertz, the longer range, increased performance, higher resolution, more functionality, and lower cost, of course, because of the integration. And again, as I mentioned, it brings in very new testing challenges that we haven't come across before. Okay, just a brief note on the second generation. So the previous one, if you saw 2017, or you were attending 2017 BITS, you may have seen Brian Nakai present the solution shown here in the lower right-hand corner. For the second generation of devices, up in the upper right-hand corner is an image of those discrete components. So in that revision, there was a separate device for the receiver, a separate device for the transmitter, and a separate device for the voltage controller. Then after these devices were tested individually, they were put into a module and tested at that. Ultimately, throughout the entire test process, there ended up being about 15 tests that were done at the various levels of integration. And many of these tests were repetitive because each time you added a layer onto the device, you had to test the quality of it. And so, there were tests done at wafer, there were tests done at film frame, at package, and then even afterwards at the transceiver module level. This, as I mentioned, was very new and expensive technology to be able to run at 80 gigahertz, take that signal all the way from the device itself out to the tester. Cabling itself was very expensive. Repeatability was an issue because anytime you touched any of the componentry, recalibration was required. The easiest way to calibrate seemed to be golden devices, but those devices would come out of calibration and need to be reset. So, there were a lot of challenges. As I mentioned, you essentially had to bring the lab bench to the test floor, along with expensive RF engineers to keep it going. So on comes the third and current generation of devices. Now, this generation did a lot of integration. So it took all those three packages that we just saw and integrated all that functionality onto the same die. So the real advantage there was package test was no longer needed. It went straight from, the wafer sliced up and became the package. So the only testing that was done at speed was in the die on the wafer. And the challenge with this, of course, is that there was still 80 gigahertz and 40 gigahertz LO signaling. But what's mentioned here is that BIST was available. So built-in self-test. And Ira mentioned this earlier. This is a real trend for applications that require a significant amount of tester resources, ultimately to gain the efficiencies in the test cell. The best way to limit the cost, the expense, the time is to build in the capability to test within the device itself. Of course, that takes up real estate within the die. There's drawbacks to that as well. But it really opened up a lot of flexibility in the test world and reduced the number of tests from 15 throughout the entire cycle down to 4. So still doing tri-temp, which of course brought some challenges, but many fewer iterations and much less repetition. So what exactly is this built-in self-test? I tried to just very simply describe a loopback scenario that is built into the device that allows this type of built-in self-test. Basically what you have, what I show on the upper right side of the screen, is a power amplifier outputting through an attenuator and back into an LNA. That's the loopback. Traditional test would have you test the PA output at a BGA ball on the package, and then test the LNA input, the receive side of the device, with a BGA source through the tester, through the printed circuit board, and through the socket. Well, when you implement this built-in self-test, now you have this loopback path. That's fine, but what we found is that implementing that loopback path left these BGA balls and the package traces out to, through the redistribution layer inside the wafer, open circuited. And so what happens when you have an open circuit is the signal bounces off the BGA ball, comes back into your source, and creates a resonance in the frequency band somewhere. Very uncontrollable, unknown specifically what frequency that's going to happen at, can have a lot to do with how far the path is out to the BGA ball, what your contacting technology looks like, a variety of different variables that impact that. And of course we don't want it. So what we implemented and what I'll introduce here is a way to terminate those BGA bumps, in this case, on the wafer. And that allowed us to eliminate any of that ringing that occurred or oscillation that occurred because of the resonance in the frequency band. Moving on here, of course, this new generation of devices brought a lot of challenges. One of them being coplanarity. Just maintaining coplanarity in a single site is a challenge, but now here, what we're doing is quad site testing at 80 gigahertz with 2 different technologies from a contacting or a probing perspective. Essentially a cantilevered beam for the high-speed signals and a pogo pin for the low-speed and powers. We ended up, noticing that the forces varied due to the cantilever lengths, due to the trace widths. There were a lot of variables that influenced the contact quality. And ultimately, there were, as I show in future slides here, we made some modifications that improved that. One of those being what's called a bridge beam with adjustability for each one of the sites from the backside of the load board. That allowed us to adjust for coplanarity at individual sites, incorporating the entire stack up from the surface of the probe head down through the PCB and into the stiffener. Site-to-site alignment, of course, was challenging. We have, again, 2 different technologies. We have to align the lead frames. We have to align the pogo pins to the device. And multi-site testing alignment, of course, CTE is a challenge doing tri-temp testing from minus 50 to 150 degrees C. The material grows and shrinks as you change temperature. And again, as I mentioned, the spring probes and the lead frame is the solution described here. We did, as I described, consider a purely spring probe with PCB transition to either a 50 ohm surface mount resistor or an absorber, a stealth absorber material that we would place on the PCB itself. Of course, we still have the 90-degree transition from a pogo pin down into the PCB, which creates a resonance at some frequency based on the length of that line. Ultimately, we went with the X-Wave probe card solution, really because it solved quite a few issues in this environment. The straight lead frame eliminated any of those 90-degree bends or transitions, and it allowed us to place the stealth technology, this absorber, directly onto the lead frame itself, which allowed us to basically suck all of that energy out of the transmission line and eliminate any of the energy from bouncing back into the die. So it solved problems that were considered very difficult at the time. But of course, it also brought new issues. The tolerances of the absorber, in some cases, limited the contact quality between the lead frame and the absorber and diminished the amount of absorption that we would have, impacting return loss. In other cases, it was too high and pushed the lead frame up, therefore causing some bowing of the overall surface of the probe card, creating challenges to keep coplanarity. So even though it solved problems, it did create some challenges as well. One thing I want to mention, we're doing 80 gigahertz test quad site here. This is a unique way to solve the multi-site high frequency test requirements out there today. Unlike the traditional X-Wave, we're actually terminating these lead frames onto a PCB. In this particular case, because of what we're doing with the loopback path and absorbing all the signal, the high speed frequencies never reach the PCB. But this technology does allow you, if necessary, to maintain that 50 ohm impedance controlled path all the way to the PCB and transition into a PCB rather than a 45 or 30 degree connector taking up a lot of real estate on the PCB. So it is an interesting and new option, for these high frequency applications. The other thing you notice is that these, if you look at the profile, these are angled lead frames. So they angle up at about an 8 or 9 degree angle down to the board where they make contact. They're approximately 25 millimeters long. So you do have to find space for these in the probe head and on the PCB. It can impact the ability to put componentry in and of course, route traces. And then one final note here is you see that we had traces on 3 sides of the device. Of course, if you try and put traces on 4 sides of the device, this particular layout is not going to function. We would have interference with the 4th lead frame. However, as you can see on the upper side of the device, the traces on 2 sides are coming out at an angle, which you could replicate on the lower side as well. But it is becoming very dense. I haven't even discussed the fact that we have all of these mounting holes and alignment pins and other things within the structure that we have to account for. I've mentioned bowing. The reason for the mounting, the significant mounting locations, is to minimize this bowing. We are using, a very rigid and robust contacting material or probe head material for this in order to maintain as much as possible the coplanarity and limit the CTE. We did have to consider all of the preload force with this large 120 millimeter or so probe head. And so by adding additional mounting, we were able to keep that coplanarity down probably around 80 microns or so, or less. And we did end up redesigning the components because in initial designs, prototype builds, the body became very thin and did allow that absorber to push it up. We designed how we split the material between the body and the retainer plate to fix that. I've mentioned coplanarity enough. Bridge beam we added. One thing I do want to mention here is, we experienced the logistics issues with going from a prototype in-house to an engineering lab at the customer to full-blown production. And, many of the things that we ran across and learned along the way, I don't have time to discuss. But it was a very important and, good experience for us, even though we did notice differences where we saw functioning hardware in the engineering location, but then when we shipped it offshore to the production, we saw the scenario shown on the screen here. So what I'm showing is simply in the red box is the initial prototype build being tested at the production site, and the red and blue boxes are the compliance windows for the pogo pins in red and the lead frames in blue. And what we're noticing here is, first of all, that they have differences at different temperatures, ambient, hot, and cold. But then they also have different windows of compliance. Basically, first contact is F to last contact is L. But the pogos have a different compliance window than the lead frames. Of course, this was a challenge. We were able to increase the compliance up to 12 mils, which is 300 microns, maxing out the compliance of the entire system. Obviously not something you want to be doing in a production environment. It did function, but we needed to bring these windows closer together and reduce the amount of compliance necessary between first touch and last touch. So we made some modifications to this structure, this profile that I described to you before, to eliminate the variability in the force that was seen at the device. We added spring dampers. So now the spring dampers all had the same force, basically a plastic pogo pin that put the same amount of force on each one of the lead frames back up into the device. That required less downward compliance to get more force into the lead frame. The other thing that was done to improve the situation of bowing was we added what we call an absorber damper into the absorber portion of the probe head. And that had a much lower force. It was more of a foam-like material that allowed this absorber to float and not place as much force up into the lead frame as we had with the absorber alone. Ultimately, we ended up eliminating the absorber damper altogether and simply adhering the absorber to the lead frame. So there was absolutely no force placed up on the lead frame. Because we did find through temperature cycling that this absorber damper actually degraded and allowed the absorber to come free of contact between the lead frame. And as I mentioned earlier, that does influence the performance. So looking at the before and after. So I showed you the compliance window before. Both of the pogos and the lead frames had different compliance windows. It extended the overall compliance window out to 11, 12 mils or 300 microns. Here, what you can see is we were able to overlap both the pogo pin and the lead frame compliance windows and reduce them down to 8 mils of compliance or 200 microns of compliance, thereby leaving us 100 or so additional compliance beyond the compliance required to get good production yield. So this was a very advantageous change that we made across all of the entire 13 probe heads that were finally delivered to production. And currently today, I think this is a bit outdated. This was probably maybe even 12 months ago. So I'm expecting that this is in the 500 1,000 insertions for some of these probe heads and probe cards that are cycling today. Some of the things that are ongoing concerns that we are still working on, and this is, although it looks like the blood, sweat, and tears that Jory, Marty, and I have put into the application, it's actually witness marking compound material that allows us to see where the bumps on the die are actually making contact with the lead frames. One of the challenges that brings is they're not contacting the ends. By design, we're not contacting the ends of these lead frames. Instead, we're contacting in the center of this channel. Well, that makes it difficult for in situ cleaning because any MyPox, ITS material will contact the end of the lead frame, not the location where the die is actually contacting the lead frame. And then the other one I mentioned, the absorber system did degrade over time, which we eliminated from the system altogether. So we look at the strengths of this solution, which there are many. And like I said, some of those apply not only to this automotive radar market, but we're implementing them today for 5G millimeter wave applications into the 54 gigahertz range. Is the excellent RF performance. It's not just the lead frame technology, but also the stealth absorbing technology that we use. The long life of the combination of pogo pins and these cantilever beams, which have almost double the compliance of a traditional probe card solution, such as a membrane style or a cantilever beam style. And again, advantages that you can replace these both lead frames and probes independently. You don't have to replace the whole set for an individual site or sometimes the entire quad site solution. I mentioned the large compliance window and the multi-site capability. So I described how we could, route these out for 4 sides. For 54 gigahertz 5G millimeter wave, we're eliminating the lead frames altogether, going with full pogo pin solutions. Peter Coburn will describe those in the poster session called our C-Racer technology. But we can apply the absorber technique for loopback into either the probe head technologies or the final test solutions for lead frames or for pogo pins themselves. Weaknesses with this type of solution, we've kind of described these as we've gone through this. It's difficult to balance, the multiple contact technologies. You saw that variance in compliance and first contact versus last contact between pogo pins and lead frames. That is a challenge to get it directly even within the micron level. Limits on the number and location of RF signals. You can see the routing challenges here by the way the lead frames are routed out. Although as I mentioned, we can implement this type of structure for pogo pins alone. In situ cleaning, it is challenging. Currently, the production solution is using brush cleaning and fixturing for MyPox cleaning instead of full in situ. And the maintenance on the absorption over time with the dampers that was required, but now eliminating the dampers altogether, there's absolutely no maintenance required for the absorbers. They are an integral part of the lead frame. Next steps, where do we go from here? So production is going on today. There's 13 probe heads. I don't recall the number of probe cards that are running in production, but they, quad site solutions have been shipped and are running in production. The methods for in situ are under investigation. Some of those cleaning surrogates have really deep, almost fibrous-like structures that may allow us to reach down to the contact point for the lead frames. The absorption system has been resolved. Control on the force has been resolved. with the dampers and the tolerance capabilities of the geometries on the lead frames. We're still working on improving alignment. This is a 0.5 millimeter pitch application, but we have done lead frame applications down to about 250 microns. And then PCB pad geometries, I haven't gotten into it, but some of the challenges are to optimize the contact to the PCB to eliminate any possibilities of shorting or creating opens due to alignment between the lead frame and the PCB. But hopefully what I've shown to you today with the advances in the IC design architectures and the contacting methodologies is a true high volume solution for 80 gigahertz automotive radar applications, as well as the new 5G millimeter wave markets. Production capable solutions with the test resources that are available on the production floors today. So that's an important point because with the loopback, none of the high-speed signaling really goes out to the tester. It eliminates the expensive cabling and the tester instrumentation required. We do have the ability to take some of those signals out, per dot location as a validation or characterization if required. And really this, hopefully demonstrated that we have built a production-worthy quad-site tri-temp probe card solution for 77 gigahertz automotive radar with built-in self-test. And again, I really want to thank NXP, for their years essentially of dedication to Cohu and the automotive radar market, since 2007. So thank you all for listening. And with that, I'll open it up if there's time.
Yeah, Jason, we have quite a time for one question.
Okay.
Did you do the calibration before an RF test? What kind of calibration do you do before an RF test?
Yes, we do. We actually have the ability in-house to measure the S parameters of each individual high-speed RF line in the probe head. So we provide, if you heard Aaron Long's presentation from yesterday, he described that we provide S parameters for each of the high-speed RF paths along with the probe head or probe card, product. We can measure just through the probe head or into the PCB through the entire probe card and through the cabling. And then we'll provide that as a calibration methodology. Or as was described, we'll provide the calibration substrates that allow you to do actual on-site calibration and even, in situ calibration. And then the third methodology that, NXP has used for some time is a golden units, where they have known good devices that they know the performance of. Simply place those into the device pocket, read the RF parameters, the characteristics of gain and noise floor for those specific devices, and then set any offsets that might be required for a production lot.
Thank you.